Well, we have seen in the Laplace domain that a convolution becomes a simple product after the Laplace transform. You'll have something very similar for the Z transform. As you can see, the Z transform of the convolution of two signals fk and gk is simply the product of the Z transforms of the underlying signals. We have seen in the previous section that if you know the impulse response h of k and the signal x of k, well, you can compute the response by taking the convolution. It will be the convolution sum, and this will be y of k. We see also here that the Z transform of this convolution is, of course, h of z x of z, and this is because of this property that we've just described. So an easier way very often to obtain the response of the signal is to compute the Z transform of h of k. This is the, as we will see later, the transfer function. Compute also the Z transform of the input signal, right? Convolution then becomes simply a product in the Z domain, and then obtain the output by simply taking the inverse Z transform. Well, we can represent this visually. So remember that if we are given the impulse response of the system and the input signal, we can obtain the output signal by remaining in the discrete time domain and computing this convolution sum. And remember that if the impulse response and the input signal are both causal, you can replace the bounds by 0 and k. So this is one approach. It's not always the simplest approach, just as in the case of the Laplace domain. It is often simpler to compute the Z transform. So the idea is that you compute the Z transform and you obtain the transfer function and the Z transform of the input. Convolution is now simply a product, okay, so it's very easy to do. And to obtain y of k, what you need to do is do the inverse Z transform, and we'll do this using an example a little bit later. Well, we can again define a concept of a transfer function of a discrete time system. This transfer function is the Z transform of the impulse response of the underlying linear time invariant system, and it can be defined as the ratio of the Z transform of the output, so y of z, over the Z transform of the input, x of z. So the transfer function h of z is the relation between the input and the output when there are no initial condition. The transfer function characterizes the system by its poles and its zeros. Okay, so by looking at the poles mostly, you can kind of have the signature of the system, and it is a very important tool for analysis and design of systems, and more in particular to design control systems, as you might see in a course like the course of digital control. So what we can do is come back to this example that we have used to illustrate the convolution sum, and this is here h of k and this is x of k, and what we can do is, well, kind of do the convolution in the z domain. Okay, so we have to first compute h of z, and then we can multiply x of z, then this will yield y of z, and what we can do here is do the inverse z transform, I will have y of k, right? Remember that the z transform of a signal f of k uk, okay, so this is the one-sided z transform, is a sum going from k equals 0 to infinity of f of k z minus k. So remember that we can write this as f0 plus f1 z minus 1 plus f2 z minus 2 plus, and of course you can continue. So if we look at this, we can easily compute the transfer function of the system. It's the z transform of the impulse response. Here in this sum there will only be two terms, so the transfer function will be 2 plus z minus 1. We can also see that x of z, the z transform of the input, will be 1, there will be 3 terms this time, plus z minus 1 plus z minus 2, right? So y of z will be the product h of z x of z, so it will be 2 times this one, so 2 plus 2z minus 1 plus 2z minus 2, and then z minus 1 times this one, so plus z minus 1 plus z minus 2 and plus z minus 3. Right? So if we have a look at the terms in z minus 1, here they are, and we also have terms in z minus 2, here they are. So what we can do now is put everything together. So we'll have 2 plus 3z minus 1 plus 3z minus 2 plus z minus 3. Okay, so what we can do now is do the inverse z transform, and we'll have the output. Well, we have to do the inverse z transform of this one. This is 2 times a delta located in 0 plus 3 times a delta located in 1 plus 3 times a delta located in 2 plus a delta located in 3. Okay, so if we have to draw this, okay, y of k, the signal is causal since we are taking the convolution of 2 causal signals, and you can see that in 0, well, if you put k is equal to 0 over here, we'll have this term contributing, so we'll have a 2 over here, in k is equal to 1, okay, if you put k is equal to 1, this term will be contributing, so you'll have a 3 over here. You'll have something similar for k is equal to 2, then it will be 1, and from there on it will be 0. Okay, so this is 0, this is 1, 2, 3, 4, and 5. And if we look at the result, we should have something similar to what we have obtained previously, and this is indeed the case. We have seen in the previous section that if the system is described by a difference equation, then it has automatically an infinite impulse response. We'll show this again here, but using the z transform and the concept of a transfer function. The idea here is that we start from, well, the simplest difference equation that you can think of, and that you have 0 initial conditions, right? So we go from this equation in the discrete time domain to the z domain by taking the z transform. So here we'll have y of z is equal to minus a. Well, here we shift by 1, 0 initial condition, so we'll have z minus 1 y of z plus b times the z transform of this input sequence x of z. So we can rewrite this as this, and we can rewrite it also as y of z is equal to b over 1 plus a z minus 1 xz. So this must be the transfer function. Okay, so this is here this transfer function, and the impulse response is the inverse z transform of the transfer function. Okay, and this transfer function we can rewrite it a little bit differently. It's 1 over 1 minus a z minus 1. And here you can see that now, well, this is the z transform of the signal that is given over here. Remember that the z transform of alpha k uk is 1 over 1 minus alpha z minus 1, and we remember that the domain of convergence is z larger than alpha. So you can see here that the b here is the one that you've got over here, and the minus a to the power k comes from this one over here, and this is what we had obtained previously. And you can see indeed that this is a difference equation that has an infinite impulse response. So the support of this impulse response is infinite, even if very often, if a in modulus is smaller than 1, it will be tending to 0, but the support will still be infinite. It is now time to discuss stability in the z domain, and this stability will of course involve the stability condition in the discrete time domain, and well, it will link it with the transfer function. This is why we need the region of convergence of the z transform of the impulse response. So it is the region of convergence of h of z, right? And remember that this is the set of all z's that can be written as a complex number under polar form, such that this sum here is bounded, such that this sequence is absolutely summable. This is another way to see this. So this is the region of convergence of the transfer function, and in the time domain, a causal LTI system, linear time invariant system, is bounded input, bounded output stable if and only if its impulse response is absolutely summable. Okay, this is something that we have shown at the end of the previous section. So what you observe is that if the region of convergence of the transfer function contains r is equal to 1, so that's the unit circle, then of course this sum is bounded, and therefore the system is bounded input, bounded output stable. Going in the other direction, if the system is bounded input, bounded output stable, then this sum converges, and you can immediately see that r is equal to 1, which is the unit circle, must automatically be in the region of convergence. This tells you that a discrete causal linear time invariant system is stable if it can be described by a transfer function h of z that has a region of convergence that includes the unit circle. And we will see in the next slide that for a causal system this condition is equivalent of requesting that all the poles of the transfer function are located strictly inside the unit circle. This is not a surprise. We had kind of seen this already in a few examples. So in order to obtain the region of convergence, remember that you take the pole with the largest radius, and here it's clearly this pole over here, and here it's this pole over here. You construct a circle with this same radius, and the region of convergence is the outside of this circle of radius, the largest radius that you can find among all the poles of the transfer function h of z. We've seen in the previous slide that, well, the system is stable if the region of convergence contains the unit circle. So this is clearly the case over here. So this system with these poles here will be stable. This is not the case over here because you can clearly see that the unit circle is not in the region of convergence. So this describes here an unstable system. You can see what happens if you take this pole and you drag it along the real axis. At some stage when you pass the unit circle, well, the region of convergence will not contain the unit circle anymore, and the system will become unstable. So you can kind of see here that indeed in the z domain you can kind of determine the stability of a system by looking at the poles, and if all the poles are inside the unit circle, the system is indeed stable. Well, this should not come as a surprise. Remember that in the S-plane, so here we have sigma and here j omega, we can determine stability by looking if the poles are to the left of the j omega axis. So j omega axis is shown here in blue, and it's also called sigma is equal to 0. And in the Laplace domain, if your system is described by a transfer function with poles to the left of the j omega axis, where the axis sigma is equal to 0, the system is stable. Let us now look at the z-plane. So what we can do is draw the unit circle. Z in modulus is equal to 1. And if we remember the relation between s and z, which is exponential of TSS, and if you remember that s, as shown over here, is sigma plus j omega, then you can write z as e ts sigma exponential of j omega ts. This will be omega, capital Omega, the discrete frequency, and this will be r. Okay, so you can see here that this axis, the j omega axis, the axis sigma is equal to 0, will be mapped to the unit circle, right? This is z in modulus is equal to 1. Okay, so it's kind of normal that imposing that in the Laplace domain the poles should be to the left of the j omega axis corresponds to imposing that in the z domain the poles of the transfer function should be inside the circle of radius 1. So what we do here is look at the dynamical behavior of systems with a impulse response that is a discrete real exponential. So alpha is real over here, and we look at the corresponding pole location of the transfer function. So we have to compute the z transform of the impulse response and this discrete real exponential, but this is something that we have done before. So you have z over z minus alpha, so you have a pole in alpha and a 0 at 0. The 0 is indicated by the circle and the pole is indicated by this cross. Well, we will not focus on the position of the zeros in this course, so let us focus on the position of the real pole at z is equal to alpha, and here we have a case where alpha is 1, so the pole is located on the unit circle. So you have kind of a case that is a limiting case, and indeed you see that the impulse response is not asymptotically stable, but it's not diverging. So what we can do is increase alpha. If we increase it to 1.2, well, the pole is outside the unit circle, so obviously, as you can see, because of this value of 1.2, the impulse response is now diverging. If you take an alpha 0.8, clearly the pole is inside the unit circle, so the corresponding impulse response will be converging to 0. We had seen previously that if you take alpha negative, well, the pole is at minus 0.8, so clearly the underlying system is stable, and this is what you see here in the impulse response. It converges to 0, but you have this alternation of signs, because you take successive powers of minus 0.8, the even powers will be positive and the odd powers will be negative. If you go to alpha is equal to minus 1, we arrive here again at a pole on the unit circle, so we're at the limit of stability. This is not asymptotically stable behavior, but it's not unstable as well. Okay, so you can see this as a limiting case, and of course if alpha is minus 1.2, the pole is outside the unit circle, and clearly you can see that the system is unstable. Because alpha is negative, you see again this alternation of signs in the impulse response. What we'll do right now is look at the systems that have this type of impulse response and make the links with the poles of the transfer function. So what we need to do is compute the transfer function, so the z transform of this signal. What you can see here is that you have a cosine. So using the Euler identity, well, you can construct this cosine using an exponential or a phasor rotating counterclockwise and another one that is rotating clockwise. This you can rewrite as r0 exponential of j omega 0 k times exponential of j phi, and here you'll have something similar, but with the complex conjugate of this one, it will be r0 exponential of minus j omega 0 to the power k exponential of minus j phi, right? So this signal can be written as a half times a alpha k plus a alpha k conjugate, right? And here a will be exponential of j phi, and alpha will be exponential of j omega 0, and I forgot the r0 over here. So the z transform of this type of signal, z transform of alpha k uk, is equal to z over z minus alpha, with z larger than alpha in modulus. Okay, so if you take this signal over here, okay, or this signal, and you take the z transform, this is what you're going to obtain, right? And if you do the calculations, this is what you obtain, but this is not so very important. The important thing is that you see that the poles of the z transform that are associated to this, well, impulse response are in r0 exponential of plus minus j omega 0. So you have to make the link between, well, the argument here and the frequency over here, and the radius that you've got over here, and this, well, damping function that you have here in the impulse response. Of course, it's also possible to compute the zeros, but this goes beyond the scope of the course. So in the next slides, what we'll do is look at this type of impulse response as a function of the poles of the transfer function. So let us take an example here, and the poles are located here at a distance 0.8 of the origin. Of course, you have the other one, the complex conjugate, and the angle here, the discrete frequency, is pi over 4. Okay, so these pole locations leads to an impulse response that is like this. Here it's a cosine. The fact that it's a cosine is linked to the zeros. Okay, this is not so very important. A cosine or a sine is just a shift, phase shift. Okay, so this will have an influence on the zeros, but the behavior will be the same. So pi over 4 is related to the frequency, and this r0, that is 0.8, well, is kind of related to the fact that this is indeed a stable signal, and, well, that this will be something that will be converging to 0 as k is increasing. This is the same signal, same poles, but it's a sine, and you see that the poles are the same. It's just a question of changing the zeros, and this has an influence on the phase shift. But again, this 0.8 is making sure that the signal is converging to 0. So here we have come back to this cosine example. The radius r0 has remained the same, but the discrete frequency has now changed to 3 pi over 4, and you see this, that you have an, well, higher frequency in the signal. In this example, the radius is 1.2 and the angle is pi over 4, and here we have taken the cosine example. This is indicated by the 0, but as I've said, this is not so important. You can see that the poles here are outside the unit circle, so of course the impulse response will diverge. Okay, but you can see that from a frequency point of view we still have the same discrete frequency pi over 4, and this r0 of 1.2 is going to make this impulse response diverge. Well, this is an example where the pole location will be such that r0 is fixed to 0.8, so the poles will be moving on a circle of a radius 0.8. We'll start with a frequency, a discrete frequency, omega 0 of pi over 12, and then increase, and you will see this in the impulse response given in blue. So pi over 12, pi over 6 here, pi over 4, you can see that the frequency is indeed increasing, pi over 3 and pi over 2. In this example, the discrete frequency will remain at pi over 4, but the radius r0, which is now 0.9, is going to increase. So this is going to dampen the impulse response because you're getting closer and closer to the origin, and this r0 that is taken to the power k is going faster to 0. 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2 and 0.1. Well, this slide gives you an overview of the types of impulse responses that you can have as a function of the poles of the transfer function. We will see that there is also an initial and a final value theorem in the Z domain, and what I will show you now is not a proof, but it's a useful mnemonic to kind of find this initial and value theorems in the Z domain. So we start with the initial and final value theorems in the Laplace domain. So we know that the limit when t is going to infinity of y of t is equal to the limit when s is going to 0, and when t is going to infinity, s is going to 0. There is this 1 over x relation between time and frequency of s y of s, and remember that there are hypotheses, right? This is the final value theorem, and you also have this initial value theorem that says that the limit when t tends to 0 of y of t is the limit when s tends to infinity of s y of s. So remember now that the Laplace transform of a unit step is 1 over s, and that the z transform of a unit step is z over z minus 1, right? And that the link between the z domain and the s domain is z is equal to, I'm going to erase that because there's no need to put a plus or a minus. So it's the exponential of TSS, right? So this is Laplace domain, and here we'll do the Z domain. So the limit will be when k tends to infinity of the sequence y of k. When s is going to 0, you can see over here that z is going to tend to 1. And s, well, we can see that, and this is how you see that it's not a proof. 1 over s corresponds to z over z minus 1, so s will correspond to z minus 1 over z y of z. Okay, and this is equivalent to the limit when z is tending to 1 of z minus 1 y z. And this is the, well, final value theorem in the z domain. And equivalently, well, you can find that the limit when k tends to 0 of y of k is a limit. When s tends to infinity over here, well, so does z. So it's a limit from when z tends to infinity of z minus 1 z y of z. But when z tends to infinity, well, z minus 1 over z tends to 1, so it's the limit when z tends to infinity of y of z, and this is the initial value theorem in the z domain. So you see here that these are indeed the equations that we have derived previously, and remember that this initial and final value theorem is used when you want to have, well, an idea of y of k given y of z, and you do not want to compute the inverse z transform of yz. So you want, or you can kind of obtain information of y of k in the vicinity of k is equal to 0. This is the initial value theorem, and when k tends to infinity, this is the final value theorem. So when you compute the initial value, well, we have to make the assumption, of course, that the limit exists, right? And for the final value theorem, we have to make sure that the, well, test that the poles of z minus 1 yz are all inside the unit circle before we use this final value theorem. If this is not the case, we could draw, well, the wrong conclusions using this final value theorem, and we had found something similar for the final value theorem in the Laplace domain. The static gain of a system described by a transfer function h of z is, well, the transfer function evaluated at z is equal to 1. Okay, so this is the static gain, and the static gain, well, we've seen this before, tells you the ratio of output and input under steady state conditions. So if the input x of k is a constant x0 and the system is stable, then the output will reach the steady state output value, static gain times x0, once all the transients have disappeared. Well, this can be shown quite easily using the final value theorem. So let us assume that we have at the input of the system an input x0 u of k. So it's a step of input x0, then x of z, if you take the z transform, will be x0 z over z minus 1. These are things that we have seen before and that by now should look familiar. So y of z will be h of z times x of z. So if we're interested at what happens in steady state, we have to use the final value theorem. So it's the limit when k tends to infinity of y of k. Okay, so this is going to be my y0 over here, and it's the limit when z tends to 1 of z minus 1 times h of, times yz, right? And this will be the limit when z tends to 1 of z minus 1, and then we'll have h of z, right? And we'll have x0 z minus 1. So this is x of z over here, right? So this will cancel out, and this will be, well, I'll write it over here, the limit when z tends to 1 of h of z times x0 z, so it will be h of 1 times x0. Okay, so we have that y0 is h of 1, h of z evaluated at z equals 1 times x0, so this is indeed the static gain. Remember that in the Laplace domain the static gain was h of s evaluated at s is equal to 0, and remember that z is linked to s by the exponential of TSS. So if you plug in s is equal to 0, we obtain indeed z is equal to 1. So it makes sense that in the z domain the static gain is obtained by considering the transfer function at z is equal to 1. Let us now illustrate these initial and final value theorems in the z domain. So assume that we are given a system that is described by an impulse response alpha to the power k uk. Alpha is real, and we'll assume that the modulus of alpha is smaller than 1, so that we have here a stable system and that we are able to use the final value theorem. Okay, so we'll consider the step response of the system that is described by this impulse response. So the input will be a step, right? So what we could do is compute y of k by considering the convolution sum hk xk. Okay, so this is going to be quite a computation. So what we could do is go to the z domain and obtain the transfer function of the system, and this will be z over z minus alpha. So please check this, because by now this should look familiar. Z is larger than alpha, and x of z is z over z minus 1, and here the modulus is larger than 1. So these are the regions of convergence of the associated z transform. So y of z is simple to compute in the z domain. It's, well, simply the product of those two. So it's z squared divided by z minus alpha, z minus 1. So what you could do is take the inverse z transform and obtain yk, but let's assume that we're a bit lazy and that we are interested in y0 and the limit when k tends to infinity of y of k. Well, then we can use the initial value theorem, and y0 is equal to this limit over here. And if you look at this yz, the highest power, the numerator is z squared, and it's also z squared at the denominator, so this limit is 1. So let us use the final value theorem. So the limit is from z tending to 1 of z minus 1 yz, so this is z squared, z minus alpha, z minus 1. Okay, remember this is yz, and this limit is 1 over 1 minus alpha. So using this initial and value theorem, we can have an idea of the step response at the initial time k is equal to 0 and at the final time when k tends to infinity. We can test this very quickly into Matlab. So alpha will say that it is 0.5. Then we can kind of introduce the numerator polynomial. It's z. The denominator polynomial, it's z minus alpha. So it's 1 and then minus alpha. And then we can use the, and because we are computing the step response, the d step response, it's the discrete step response num den. And this is what we have here. Okay, so we see here indeed that in 0 the response is 1 and it tends to 2. So this is indeed equal to 1 over 1 minus alpha. So 1 over a half, which is 2. Well, we will now start a subsection on the inverse Z transform. It's very important to master this inverse Z transform because you need it to go back to the discrete time domain. So one of the methods that can be used is the so-called long division. So if you have a rational transfer function h of z, you can obtain the following description by doing the long division of the numerator polynomial divided by the denominator polynomial. And once you have this description, well, you can do the inverse Z transform, and this is what you obtain. So this is a constant, so it's Z transform, it must be the Z transform of a delta. So this is a constant times Z minus 1. Well, it must be the Z transform of a delta that has been shifted by 1. Okay, so once you obtain this, it's quite easy to obtain the inverse Z transform. So we've seen previously that a system that is described by a difference equation has an infinite impulse response, and we've used this very simple difference equation to show that indeed the system that is described by this difference equation has an infinite impulse response. So we'll do it again over here using the Z transform and as an illustration of the long division. Okay, so first of all we need to compute the transfer function. Remember that if you take the Z transform, you'll have y of z is equal to minus a. We shift to the right, so we'll have z minus 1 here, y of z, and here we assume 0 initial conditions plus bxz, so we can rewrite this as 1 plus a z minus 1, y of z is equal to bxz, and indeed you see it here that the transfer function is given by this expression. So what we'll do now is divide the numerator polynomial by the denominator polynomial, and here you have to organize everything to have the highest power of z at the front. So this is z equals z to the power 0, and this is the highest power. So here we work with the variable z minus 1. You will see that in the next slide we work with the variable z, because this transfer function you can also write it as bz z plus a, right? So here we work with the variable z minus 1, and we see that if we simply take a b here and we multiply by this one, we have b plus ab z minus 1. We subtract and we have minus ab z minus 1. So the next term will be, well, we have 1 over here, minus abz minus 1 over here, so we need minus abz minus 1. Okay, so we multiply with this term, so what you have is minus abz minus 1 plus, minus a square bz minus 2. If we subtract, we have here a square bz minus 2, and well, you can see that the next term will be a square bz minus 2, and you can keep on going. This is why it's called a long division. It's a very long division, right? So this will yield here an expression of a z that is easy to for which it's easy to compute an inverse z transform. So indeed, this is the expression of h of z, and if you compute the inverse z transform, this is what you obtain. So this is indeed the z transform of a delta located in 0, so b times a unit impulse. This is a unit impulse but shifted to the right, so you have minus ab delta k minus 1 and so on. But this impulse response, you can rewrite it like this, and you can check that this is indeed the case. h0, if you compute it by this expression, well, in this sum there will be only one term that will be contributing, the first one, so we have b, and if you plug in k is equal to 0, and here you have b also. H of 1 will be, if you look at this, there's only this term that is going to contribute, so minus ab, and indeed if you plug in k is equal to 1, you have minus ab, and you can keep on going on. So we have shown that this is the impulse response, and this impulse response has indeed infinite support, so it is an infinite impulse response, and this time we've chosen long division to prove it. You can also work with the variable z. Remember that you can also rewrite this transfer function as follows, and then you have to organize this division in such a way that again the highest degree in z is in front, and you will see that this will kind of organize the coefficients in the same way, and you'll proceed exactly as in the previous slide as is shown over here. Well, we have seen that one inverse z transform method is the long division, but what is used by far the most is of course partial fraction expansion followed by inverse z transform of, well, these partial fractions, right? So the basics of partial fraction expansion are the same for the z transform as for the Laplace transform. Beware that the transfer function must be strictly proper, okay? And if this is not the case, well, you have to do Euclidean division to make sure that this condition of strict properness is met, right? To do the partial fraction expansion, well, you have to compute the poles, and we will see that the expansion can be done both using the variable z and using the variable z minus 1. And once you have the partial fraction expansion, the inverse transform can be used using the z transforms that we have considered in this course. So there is only one z transform that you will not have in exercises at the time of the exam. It's the z transform of a sine or a cosine. So what we'll do here in the next two slides is take the inverse z transform of y of z, and this is the y of z that we are considering. Here we are expressing it as a function of z minus 1. But if you multiply the numerator and denominator by z squared, you can also rewrite it like so. And here we express y of z as a function of z. So sometimes what we do is write y of z over here, and here we write y of z minus 1, just to show that here we consider the z transform using the variable z minus 1, and here it is using the variable z. So in this first slide we'll work with the variable z minus 1, and we'll do the partial fraction expansion of y of z minus 1. So we'll consider this expression here, y of z minus 1, right? So we have to check if we have to do Euclidean division. So we have to check if this expression is strictly proper. So you have to remember that the variable is z minus 1. So here the degree of the numerator is 1. It's the highest power of z minus 1, and the denominator, the degree is 2. The highest power of z minus 1 is 2, which yields z minus 2. So no, it is not necessary to do Euclidean division. So what we do is do the partial fraction expansion just as we have done before, right? So we have a second order at the denominator. We expect two constants. Here they are, a and b, and as usual what we do is compute a by which is the numerator to this rational function over here, by hiding this one. Okay, so a is this one divided by this one, expressed at the root of the denominator. So this is z minus 1 is equal to minus 2. So if we inject this in here, we have minus a half. And if we do the same for b, okay, so what we do is hide this one over here, right, and we obtain this one divided by this one at the root of the denominator. So it's z minus 1 is equal to 2. You can see that this is indeed the root of the denominator. If we inject z minus 1 is equal to 2 in here, we have 3 over 2. So this is minus a half, and this is 3 over 2 over here. So what we can now do is do the inverse z transform. So the first term is the inverse z transform of this one over here, right? Remember that the z transform of alpha k uk, this real exponential function, is z over z minus alpha, and it can also be written, and it's more appropriate here because we work in the variable z minus 1, as a 1 over 1 minus alpha z minus 1. So 3 over 2, here we have got it, and this is the z transform of the sequence 1.5 times 0.5 to the power k times uk to make everything causal. It's important to multiply by the unit step, just as we have multiplied by the unit step in the Laplace domain. So this one here, minus a half, here it is, minus a half, and this one is the 1 over this thing here is the z transform of minus 0.5 to the power k times the unit step. So this is the inverse z transform of y of z, and here we have worked with the variable z minus 1. What we'll do now is work with the variable z instead of z minus 1. So we'll work with y of z, so with this expression over here. And when you work with the variable z, in this case there are two methods, and the first method is to work with y of z divided by z, and in my opinion this is, well, in this case the easiest way to go. So y of z divided by z is, as you can see, z plus 1 divided by z plus 0.5 and z minus 0.5. Obviously y of z divided by z is strictly proper. By the way, this is not the case here of y of z, and in the next method we'll work with y of z directly. So the first thing that we'll have to do is a Euclidean division. So if you work with y of z divided by z, everything becomes strictly proper, so no need for an Euclidean division. So you can do the partial fraction expansion, and these are the two terms that you will have. Second order at the denominator, two constants a and b. And once you have done the partial fraction expansion, well, you can see that y of z will give this expression here, and these are transforms that are well known. Okay, so this is why you work with y of z divided by z. When you will multiply by z, you have here something that is easy to work with. Remember that the z transform of alpha k uk is z over z minus alpha. So if we decompose in partial fractions, well, we can compute a as usual. We forget about this one, and we take z plus 1 over z minus 0.5 at the root here. Z is equal to minus 0.5, and if you inject, you'll have minus a half. And for b we do something similar. We hide this one, so we have this expression here that we evaluate at the root here. Z is equal to 0.5. If you inject, you have 3/2. So here we have minus a half, and here 3/2. And if you do the inverse z transform, this is what you obtain, and this is of course exactly the same result as when you work with the variable z minus 1. So in this case we'll work again with the variable z. So we'll take this expression, but we'll work with y of z directly. So observe that this y of z is not strictly proper, because the degree of the numerator is not smaller than the degree of the denominator. So we need to do a Euclidean division, right? So let's do this. So we have to divide the numerator polynomial by the denominator polynomial. Okay, so if you multiply these two, you'll have z squared minus 0.25, and here if you multiply, you have z squared plus z. So this is why we divide like this. So this polynomial times this one time will produce z squared also, so that's okay. So we write z squared plus 0z minus 0.25. We subtract, and we have z plus 0.25. Okay, so you can see that y of z is 1. This is what you have got over here, and then this one, the rest divided by this polynomial, and this polynomial is of course z plus 0.5 times z minus 0.5. So this is how we arrive at this expression, and this expression is now strictly proper. Okay, so we can do a partial fraction expansion of this one. So you can write it as a over z minus 0.5 and b plus over z plus 0.5, and I'll leave you the computation of a and b as an exercise, but you'll arrive at a is equal to 0.75 and b is equal to 0.25. Remember that the z transform of alpha k uk is z over z minus alpha. So when you look at this expression here, well, there is no z. So if you introduce the z, you'll have to put a z minus 1 and a z minus 1 over here. Remember that this is the delay operator, right? So when we do the inverse z transform, this is what we'll obtain. This is the z transform of a delta, and here we'll have, well, 0.75 times this one. Here you have a delay operator, not times k, but times k at the power k minus 1. You will have 0.25. If you look at this expression, you see that this is z minus 0.5, right? So it's 0.25 minus 0.5 to the power k minus 1, because we have a delay operator. And because the delay operator, of course, we have here a step that has been delayed also. Okay, this makes sure that, well, this part of the response starts at k is equal to 1. So we see here that the expression is different than the two expressions that we have obtained previously, but we will show that they are equivalent in the next slide. We have seen that with this last method we have obtained a expression that is a bit different, and what we intend to do here is show that it is equivalent to the expressions that we had obtained previously. So first thing that we do is replace the exponent k minus 1 over here and over there by k. So this means that we have to, well, here divide by 0.5 and here divide by minus 0.5. So this will yield 1.5 over here, and here it will give us minus 0.5. All right, so this is how we obtain this expression over here. Now we are going to replace uk minus 1 by u of k. So it will be correct for every k except k is equal to 0. There we'll add something, and if we evaluate this expression in k is equal to 0, you will see that this will yield a 1. So in k is equal to 0, we have to correct and we have to subtract this 1, and this is done by subtracting in unit impulse, and because this will subtract 1 when k is equal to 0, and of course the deltas will compensate, and we obtain the expression that we had found in the, well, earlier methods, and the one that works with z minus 1 and the one that works with z, where you do the partial fraction expansion y of z divided by z. We have seen that the response of a discrete time system can be described by a difference equation. If the system is LTI, well, we'll have a linear difference equation with real coefficients, such as here shown on the screen. Well, to solve this difference equation, we'll have to go to the z domain, and of course this will involve initial conditions y of minus k for k going from 1 to n, right? After z transform, you obtain this relation, and this relation looks a lot like the relation that we had obtained for linear time invariant but continuous time systems that were described by differential equations, and you had exactly the same equation but with z replaced by s. So here y of z is the z transform of the output, x of z is the z transform of the input, I of z depends on the initial conditions, and the polynomials a and b are given over here. It's quite easy to obtain this, because if you take the z transform of this, you have z minus m y of z, and then you'll have the influence of the initial conditions. Okay, so this is how you obtain, for instance, the polynomial a of z. So once you have the response in the z domain, well, you can obtain the complete response in the discrete time domain. This is just involving a inverse z transform, and we have just seen how you can do this, and of course this will involve partial fraction expansions. You see here that this complete response is the sum of two terms. The first one is the zero state input. It's the response where the initial conditions are zero. It's the response that comes solely from the input. Okay, so in French it's called la réponse forcée. The second term is the zero input response. This is the response when the input is zero, and it's the response that is coming purely from the initial conditions, in French la réponse libre. And you know that the relation between y and x when the initial conditions is zero is the transfer function. So this is the transfer function, and as you know, the transfer function here is the z transform of the impulse response. So here we have to solve a second order recursive or difference equation. The initial conditions are given over here, and when we go to the z domain, well, we have to take the z transform of these two over here, and this is the result, and we have to take into account these initial conditions that are given over here. So you'll have to do this at the time of the exam, and well, you better not learn this by heart, otherwise you'll make mistakes. So let us have a look if we can kind of obtain this in some way. So let us draw an example over here. So I will work with 3 colors. So this will be my signal y of k, and what we'll do is take the z transform of y of k uk, just to indicate that it's a one-sided z transform, and it's the sum when k goes from 0 to infinity of yk z minus k. If we write the first terms, it's y0 plus y1 z minus 1 plus etc. And this is y of z. This is, when we take the Laplace transform of this one, this is y of z, right? So now we have to work with the shifted versions by 1 and 2, right? So let us first draw the one where everything is shifted by 1. Here it will be shifted by 2. So the red one will be drawn over here, here it will be drawn over here, and the green one will be over here, and here it will be located over there. So we can kind of see what is happening. So let us compute the z transform of yk minus 1. The sequence shifted to the right by 1. It's still a one-sided z transform. So we need to multiply by u of k, and the definition is yk minus 1 z minus k. And if we look at the terms, we'll have a term that corresponds to k is equal to 0 is y minus 1. This is correct. The red one that is over here has been moved to this position, so it's multiplied by z0, but it's obvious from this formula over here, plus term that corresponds to k is equal to 1 now, y0 z minus 1, plus term that corresponds to k is equal to 2, y1 z minus 2, etc. If you compare with what you see here above, well, this is z minus 1 y of z, and you have to add this term over here. So this is indeed correct. So let us do now the z transform of the signal shifted by 2. It's again a one-sided z transform, except that now we have to work with the signal shifted by 2. Term that corresponds to 0, y minus 2 times z to the power 0, 1, plus y minus 1 corresponds to k is equal to 1 here, z minus 1 plus y 0 z minus 2 plus y1 z minus 3, etc. And this term corresponds to k is equal to 3, this one to k is equal to 2. If you compare with what is above, well, this is z minus 2 y of z, and we have to add these two terms, y minus 1 z minus 1 plus y minus 2, and this is exactly what you've got over here. So you can see you don't have to learn this by heart. It is easy to obtain from the definition of the z transform. We've just computed the z transforms of y of n minus 2 and y of n minus 1, and of course don't forget the z transform of y of n, which is simply y of z. So here we collect all the terms in y of z. I've got one over here, and well, minus 1 over here. So this is indeed correct. We take all the initial conditions on the other side. Notice that I've written here a parenthesis, so this 6 should also multiply what's inside here, right? So initial conditions go on the other side, so here you'll have z minus 1 minus 1 over 6 and plus 1 over 6. So this is indeed correct. So y of z is this one divided by this one over here, and this polynomial has been factored. Please, when you factor, check that everything is correct, and you can see here that this is indeed the case. So this is how we obtain this expression. What we'll do is change signs here, because remember that the z transform of alpha k uk, so this exponential sequence, is 1 over 1 minus alpha z minus 1. So we like to have 1 minus something, so this is why we change sign. And what we do over here is compute the partial fraction expansion, and I'll leave it as an exercise. Do not forget that when you have done the partial fraction expansion, you should check if you put everything under the same denominator, you should again obtain what is over here. Well, after partial fraction expansion, what we have to do is compute the inverse z transform, and this yields the following relation. So we are not done yet. We should check if this solution is compatible with the initial solution. So what we can do here is notice that y of n is equal to 6yn minus 2 plus yn minus 1. So y of 0 is 6 times y of minus 2 plus y of minus 1. And once you have y0, you can also compute y1. You notice that I have put n is equal to 0 in this equation, and to have y1 I plug n is equal to 1 in here, so I have 6 times y minus 1 plus y of 0. Okay, and y of 0 has been obtained by this equation. So if you plug in these values, this is what you obtain here. So you can compute the values of y in 0 and 1. Okay, so now you can check if this is indeed correct. And indeed, if you plug in 0, n is equal to 0, you have a 0 over here, and n is equal to 1, you'll have minus 5 divided by 5, so this is indeed minus 1. So we have a solution here that meets the initial conditions. In example 2, we have a first order recursive equation, and notice here that the time shifting is to the left. In a real physical system, we have seen that this involves recursive equations with time shifting to the right. In some cases, some applications, you might be confronted also with recursive equations with shifting to the left, and here this is the case. When there is time shifting to the left, you will see that it is more natural to work with the variable z, and in the previous example we were doing time shifting to the right, and there it's more natural to work with the variable z minus 1. Okay, so again we'll have to go to the z domain. So the z transform of yn is y of z, and the z transform of yn plus 1 is zys minus zy0. So again, this is something that you should be able to obtain at the time of the exam without learning it by heart. So let's see if we can find this relation. So again, here I will draw an example. So this will be our signal y of k, just as an example. So the z transform, and we'll use again, of course, the one-sided z transform, otherwise we would not be able to work with initial conditions, is the sum of k going from 0 to infinity of yk z minus k. This is y0 plus y1 z minus 1 plus y2 z minus 2, and this is equal to y of z, right? So let's shift this now to the left. So the blue one will be over here, the red one will be over here, and we'll have something like this. Notice that everything has been shifted to the left. So now we consider the signal z transform of yk plus 1. It's still a one-sided transform, and we have to therefore consider a sum where k goes from 0 to infinity of yk plus 1 z minus k. The first term when k is equal to 0 is y1 z to the power 0. Okay, so indeed it's y1 that you see here. It's the first in this shifted signal. It's the first signal that corresponds to an index 0. So you would have y1 z0, and this is indeed what you got. So you can see it from here, but it's easier from this equation here. So this is the term that corresponds to k is equal to 0. If we consider the term that corresponds to 1, you will have y of 2 z minus 1, etc. Okay, and you can clearly see that you can obtain this thing here by multiplying this thing, so y of z by z. But if you do this, there will be one term that is not in here. It will be z times y0, so you have to subtract this. So again, you see that this is correct. We are able to find this relation without learning it by heart. So we will have to work with the z transform of this signal. This looks a bit weird, but this is n u of n plus u of n. Okay, so we need to take this z transform and this z transform. Okay, this is something that we had seen when we had considered the derivative of a z transform. Remember that if the z transform of alpha k uk is z over z minus alpha, it is possible to obtain the z transform of k alpha k uk, and this will be minus z, the derivative of this one. Derivative, of course, with respect to z, and if you make the computation, it will be alpha z over z minus alpha squared. Okay, so this is a step. Alpha is equal to 1, so the z transform of this one will yield this, and the z transform of this one. Okay, well, notice here that we have used the index n, but you can use any name for the index, right? Usually in the course we have used k, but here for a change I've used n, so this should not disturb you, right? So this is how we have obtained this relation over here, right? So what we can do now is isolate everything that has to do with y of z. So you'll have 1 over here and minus 2 over here. This is what we obtain, and this one will be going on to, no, this one here will be going on the other side with y of 0 is equal to 2. What is done over here is that everything is put under the same denominator, right? And then, we divide by z minus 2, and we obtain this relation over here. This term here comes from the initial conditions, and this term here comes from the input. Okay, so this is the 0 input term, and this is the 0 state term. This will be la réponse libre, and this will be la réponse forcé, right? So once we have y of z, we can do the inverse z transform, and the easiest thing to do, well, this thing is, well, kind of obvious. We already know what its inverse z transform will be. It's a well-known z transform. For this one here, what we'll do is divide by z. We'll use this first method when you're working with the variable z. We divide by z. This is what you obtain, and now you do the partial fraction expansion. You'll have, well, a third order at the denominator, so you need three constants, a, b, and c. And if you compute a, b, and c, I'll leave this as an exercise. These are the three terms that you obtain. Again, do not forget to check this by putting everything under the same denominator and see that you obtain this again, right? So so now you can of course obtain y2 by multiplying by z. This is y2 over here, and this is y1 of z. So you see that you have terms in z minus 2 over here and over here. So of course we're able to group them. So here indeed the two terms with the z minus 2 at the denominator have been grouped. Remember that the z transform of alpha k uk is z over z minus alpha, and that the z transform of k alpha k uk is alpha z z minus alpha squared. Okay, so it becomes now easy to do the inverse z transform. And of course we are not done when we have this solution. We have to check that this solution meets the initial condition, and if we plug in n is equal to 0 over here, we can see that this is indeed the case. So we'll have 4 minus 2, so it's indeed a 2. So this is compatible with the initial conditions. As a summary, this slide shows you the link between the Laplace, Fourier and Z transforms. We have seen in section 5 that you can obtain the Fourier transform from the Laplace transform if sigma is equal to 0 is in the region of convergence of f of s. This means that f of s converges on the j omega axis, so you can simply replace s by j omega. In this section 8 we have seen that, well, if you sample the signal, you can consider the Laplace transform of this sampled signal, and this leads to the Z transform with its definition over here. This is the two-sided Z transform, by the way, as we have here the two-sided Laplace transform, and the link between the S and the Z domain is given by this relation. In the next section, well, we'll fill in this blank here, and this will give rise to the discrete time Fourier transform, and then we'll see a last transform, which is the discrete Fourier transform, and its algorithm to implement it, the fast Fourier transform. I have skipped a few slides on the sampling of a cosine signal. These slides are there for your information, so feel free to have a look. And here, of course, we're illustrating what you can do with Matlab. And of course, some of you will have the separate Matlab activity, so please attend and participate actively. In here, so a system with transfer function z plus 1, this is what you can see here, and at the denominator z minus 0.5, z minus 0.7 is considered, and the sampling period is 0.1 of a second. So then the impulse response is computed, the step response, and then the input to a sine. So the response when the input is a sine, and well, finally the Bode diagram is computed. So this is the impulse response, the step response, the response to a sinusoidal input. You notice that the input has amplitude 1. And this is the response. Here we have the Bode plot, and in orange the input, or the frequency of the input sine from the previous slide is indicated. So you can see that you should have at the output a amplification of roughly, well, 23-24 dB, something like that, and a phase shift of minus 20 degrees. And you see that more than 20 dBs corresponds to an amplification of more than 10, and this is indeed the case, and you can see this small phase shift of 20 degrees. It is also possible to compute Nyquist plots, although we have not focused on this in this course. They will come back in more control-oriented courses. It is also possible to discretize a continuous time system and obtain a, well, transfer function in the z domain. This has not been tackled in this course, so it's for your information. And it is also possible using the symbolic toolbox to compute z transforms, and for instance using this command over here, and compute inverse z transforms. Well, of course, you can also work with Python, here again in this JupyterLab environment of the Anaconda environment. So here you have a first example where the control package is used. So you can see that the same example is used as previously, and it's possible to compute the impulse response, the step response, the response to a sine, and to compute the Bode diagram. It is also possible to work with another package, and this is what sometimes makes it a bit more difficult in Python. You have different packages you can work with. This is with the SciPy signal package. So the system is introduced like this, and again you can compute the impulse, step response, the response to an input signal, which is the sine over here, and compute the Bode diagram.